Thank you, David. It gives me great pleasure to be back speaking at this Finding Petroleum event. My talk today will focus on the visualization and analysis of 4D seismic with particular emphasis on its role in history matching. So what I'm going to be looking at is the top of Habib's pyramid, the integration. Once the data has been made available, how you actually use it and integrate it with data from other sources. For those of you who don't know me, my name's Jane Wheelwright, and I work for Dynamic Graphics. And I'm going to, for my sins, be giving a live demo. I advocate widely that rather than using PowerPoint as an integrating tool in the oil and gas business, there's the requirement for something a little bit more sophisticated. So the system that I'm going to be showing is called CoVis 4D, and it's a vendor-neutral visualization and analysis system that allows data to be brought in from multiple sources, from Landmark, from Schlumberger, and across the range from input seismic through to production. One of the key features of the software is its capability to incorporate temporal data from a variety of sources. So this could be 4D seismic, simulation, temporal attributes, microseismic. So any data that has a timestamp can automatically be amalgamated together. The argument for the use of 4D time-lapse seismic for monitoring a reservoir is now widely accepted, although it is unfortunate that while it has been accepted, companies haven't really been prepared to put their money where their mouth is. So the actual take-up, which I would have expected 10 years ago to be much more rapid than it has been quite disappointing. And I think it does all come back to this value that's perceived to be in taking up the technology, not in terms of the actual theory of whether it's a good thing or not. So 4D seismic provides a means of determining the changes occurring in the reservoir as a result of hydrocarbon production or water gas injection by comparing the repeated data sets. Interpretations of reservoir pressure saturation and fluid contacts from time-lapse seismic contribute to production enhancement by constraining production, history matching, and enhancing reservoir simulations. I was at a recent 4D SPE workshop, and Colin Macbeth remarked that 4D time-lapse seismic should really always be used unless there's a very good reason not to be. There are certain cases where permanent monitoring isn't necessarily going to benefit certain reservoirs, such as carbonate and clastic fields, but in many instances it can give great insight into changes and fluid movement over the life of a field and indicate the consequences of the current drilling and injection regime. It's the most valuable tool for providing accurate history matching with the predictive simulation model. Just to briefly summarize a bit of history matching. History matching involves the integration of dynamic data into predictive simulation models. Time-lapse seismic data is a vital source of information to provide the best matches. However sophisticated a model is, it's only a representation of a field, but an accurate history match can validate a model and support its use for future planning and decision making. So this talk is going to look at the collaborative use of 4D seismic and simulation data specifically to improve reservoir planning. And what I want to include is the generation of petroelastic properties in the simulation model and their role in generating synthetic seismic to accurately and quantifiably compare with the observed seismic. One of the major issues with history matching in the industry today is the lack of tools for integrating seismic and production data. If you're looking at one or the other, the tools are pretty good for actually monitoring changes either in the seismic or the simulation. But there is a real dearth in actually having something that will truly integrate the different data types. What's required is a truly quantitative approach to determine the accuracy and relevance of a predictive simulation model with reference to the monitor seismic surveys. History matching has a critical role in monitoring displacement processes, constructing good reservoir models, and predicting future performances. So just to sort of briefly summarize my talk, the key thing I want to do is actually sort of show the data integration, to show visualization and analysis specifically of 4D seismic and simulation. The key thing that I want to cover today is the problems when you're working with data that overlaps, but has different geometries and is of different types. There are different scales. The key thing, if the requirement is to actually quantify differences between the two, is that one set of data has to be back interpolated in the other, so that both pieces of data are in the same object. And this then allows cross-plotting of the data and actually quantifying the differences between them. So leading on from this, I want to just show how simple it can be to generate a petroelastic model, and from this create synthetic seismic at the same time steps as the observed seismic. So this is probably the most important way of actually seeing whether your predictive model is matching your expectations, and using this for reservoir management. So the first issue you have with temporal data is that normally the time steps will be different. So what we're seeing here is a 4D seismic model and a simulation model showing water saturation. And you can see the changes in the simulation don't match the changes in the seismic data. So what we have with this particular system is that any data that's loaded into the viewer is automatically added to a global time slider. So this data could be anything with a timestamp. It can show a well as it's being drilled. It can show seismic attributes changing over time. We're obviously here looking at simulation and time-lapse seismic, but any type of data with a timestamp is automatically added to this list. But what is key is if there is a discrepancy, a large discrepancy in the time steps, that they can be added or subtracted as required. So if you're looking at production on a daily basis, you're looking at 4D seismic, which is over several years, you may just want to see what the data looks like at the time steps in your time-lapse seismic. So that's exactly just what I'm going to do here. I've taken the reservoir simulation steps out of the equation. So now we're just looking at the water saturation value at the time, at each monitor survey step in the 4D seismic. So this is just a very sort of simple way of just showing how data is integrated. So a key thing, if you want to actually not just look at observe the changes, but actually to have a better understanding and actually quantify the differences, what is required is that the data from one object is back interpolated into another. So this allows a direct spatial comparison between data sets. And this is particularly relevant when data is overlapping but spatially non-coincident. It's important that the values of one property in one can be put into the other. This means that the information from both data sets is consequently in the same object and can be statistically analyzed, and the results from this can be put back into other processes. So once the data is in the same object, a cross-plot can be generated with an optional coloring from a third property. The input can be a file with back-interpolated property. From this, the statistics that can be generated from this object include linear regression lines, and it's possible also to pick up points which lie outside the regression lines. So this allows you to identify the areas of a model which are not matching, and being able to use that information to put back into the simulator or in other processes. So it allows a statistical comparison of multiple data sets, and also, very importantly, the export of the results. So just in very simple terms, we have here a gamma ray well log and the same 4D seismic and simulation grid. So in terms of back interpolation, so the key thing is to ensure that the data is available in a single object. So if I, for example, want to input the seismic into my log file, it's just a simple question of picking up the log data, importing an attribute, and I'm going to import the time-lapse seismic. So it's an instantaneous operation. So I now, in my log file here, I now have a new property which is time-lapse seismic amplitude. So I can cross-plot my time-lapse seismic against any of the attributes in my log file. Looking at history matching, the important thing is to be able to actually do this in terms of the simulation data as well as the seismic. So in exactly the same way, I can pick up my simulation grid, import an attribute, and again import the time-lapse seismic. So what I'm seeing here is the time-lapse seismic as a new property in my reservoir simulation model. And again, if I scroll down, I'm just going to filter on my temporal properties. So I now have a new property, which is time-lapse seismic. And because that's now embedded, it's now a new property in my simulation model, I can now do statistical analysis on it. So I can pick up my simulation grids and generate a scatter plot, and I'm going to cross-plot my time-lapse seismic against my water saturation. And this data is linked directly to the viewer. I can apply a regression line and put in sigma lines, and I'm just going to change the color. So I'm going to color by water saturation so you can see the options more clearly. So if I want to, for example, identify values that lie outside my sigma lines, I can immediately pick them up in the viewer. If I reverse the visibility, I can delete those points. And these individual IJK locations, which are a poor match, I can export to an ASCII file and use that as input into another run in the reservoir simulation process. So this is just so what I've just done is back interpolate the seismic, the 4D seismic. And because it's a 4D seismic, it's a temporal property, the results are also temporal as well. So you get the 4D for just as embedded into the actual export. So at the moment, what we've been looking at is a comparison between the seismic and, in this case, the water saturation in the simulation model. What is probably far more useful is actually to be able to compare something more like with like. And one of the, in fact, the new capabilities with the software, we have a Sim-to-pem and a pem-to-size workflow. So what this allows to be done is to generate a petroelastic model within the simulation grid, and from this to calculate synthetic seismic, and the synthetic seismic can then be compared back against the observed seismic to again check in terms of history matching. This is a very good way of making sure that how the predictive model is expecting the reservoir to behave, that it's actually going according to plan. So the first part of this workflow, the Sim-to-pem section of the workflow, the input is a simulation grid with reservoir properties, so porosity, net to gross, pressure and saturations. Alongside that, you also need the standard rock physics parameters such as grain bulk moduli and the fluid properties. From this, you calculate the petroelastic model, which is the S wave and P wave velocities and the bulk density. This is run for every cell in the input grid. If there are static regions available in the simulation model which represent different physical properties, these can also be used. And it's repeated for every chosen time step in the input reservoir simulator grid. The pem-to-size, once this petroelastic model has been generated, generates synthetic seismic from the petroelastic model. And this enables a comparison of the synthetic with the observed seismic for improved seismic history match. And the output is a 3D grid of the computed seismic response based on the petroelastic properties and wavelets. And the key components here, because the generation of the synthetic seismic is done in time, so an integral part of the actual workflow is a depth to time conversion, and then if required, a time to depth back. So if your initial observed seismic is in depth, you need to be able to convert your synthetic seismic back to depth. And this then generates the synthetic seismic generation. So just a brief schematic. The input is, I think you can see the cursor, is a cell grid, which is in general would be converted from depth back into time with the calculation parameters. This creates an extended elastic impedance. It's sampled in seismic space by a seismic template in time, so this gives the dimensions of the resultant grid. And there's the option to generate an impedance output or a reflectivity output. If it's an impedance, it's convolved with a wavelet to generate the synthetic seismic. So what I'd like to do is just go through the process of running that, and I just have a data set to hand, and I'm just going to, just as a startup, input the simulation grid. So this is a simulation grid. At the moment we're looking at ternary colours, oil, gas and water. So the first step is to generate the petroelastic model. So to do this, I'm going to run a module which we call Sim-to-pem, and I'm inputting the grid that we have open in the viewer at the time. And if the properties are correctly named in the grid, it will read them automatically. So we have oil saturation, gas-water saturation, net to gross, gas-oil ratio, porosity and pressure. And I'm just going to load a parameters file. And this loads the rock and fluid parameters for 5 different regions. So the parameters are the rock properties in net fraction, non-net fraction. By default, we're using a Batzel-Wang for the fluid properties, but it's also possible to have user-entered formulas. So if you want a Hark formula, if you have something that's a proprietary formula, that can also be added. And we're going to calculate, and it's very, very quick. So we have now calculated those properties. So now if we look down through the properties, we now have a P wave, an S wave, which we can colour by those properties if we want to see them. And we also have this bulk density property as well. So we've now created our petroelastic model in our simulation grid. So with this, we're going to calculate synthetic seismic and compare it against the seismic that I showed earlier. So we're now using the second module, which is the PEM to size part of the interface. And I'm going to again load the model that we've just created. And I have again a parameters file. The advantage of having a parameter, I could type in every value in the interface. The issue there is spelling mistakes. It's often better actually to have a text file set up. It's much easier to go in QC and make sure you've put all the right values in. So what the parameter file has done is it's specified which dates are required, and these dates for the synthetic seismic are going to match the observed seismic that we already have. It also sets up all the constants and the background shale values that are required for this particular data set. And for example, there's a chi of 17 degrees, which best represents the fluid properties of this particular model. Because the calculation is going to be done in time and the model is in depth, I'm going to apply also an average velocity grid. And I need a seismic template just to show what the range of the output seismic is going to be and what the spacing. And because I'm creating the synthetic seismic, I also need a wavelet. I'm just going to put a bandpass trap. And we can have a look at the wavelets. So if you've got multiple wavelets, you can make sure that you've got the correct one being used. The seismic, the observed seismic that we have is inverted, inverted in seismic impedance volumes. So the output option I'm going to take is the band-limited impedance, which we'll compare with the two. And I'm going to convert the synthetic back to depth because my original seismic is already in depth. There's also the options to save the data in SegWi format and select dates for a different grid, but I will just run like that. So this is a fairly complex process. What we're doing is converting the original simulation grid to time. So all the calculations for the synthetic seismic are being done in the time domain. When the calculations have been made, there'll be 3 volumes of seismic, which will represent the dates that I've got here. And then the synthetic seismic will be converted back to depth. So this is all being done in real time. There's no sleight of hand here at all. And that now has run. So I'm just going to add the group to the data registry, and we'll go and check the results. So actually what I want to do first is to start with, I've already got, knowing that I wouldn't have a huge amount of time, I've already back interpolated the observed and the synthetic seismic into a simulation grid. So this PEM with seismic has the synthetic seismic and the original 4D seismic impedance back interpolated in exactly the same way as I did earlier when we had the simulation grid and the seismic up. So in terms of actually comparing the two, they are both now intrinsic properties within the simulation grid. So if I go back now to the statistical tools and do a scatter plot, I can now plot the two against each other. So this is giving a much more realistic comparison of the two different data types. So we have the original observed seismic and we have the synthetic seismic that's been created from the petroelastic model. And you can see there's a pretty good match. So again, we can put in a regression line, we can put in sigma lines. Again, we can pick up the data that does match and select those data points, highlight the good match. We can reverse the visibility and take out the points that match well and save the values. I'm just going to put the values back in and just change the sigma lines a little bit so we can isolate the points. Again, go back to select the points. So again, I'm picking the points that do match relatively well and then just removing those from the equation. So what we have now in the viewer are the cells where the match is the poorest. So it may be down to transmissibility problems, it may be down to unexpected flow problems, it may even be problems with the actual drilling or injection regime, there may be problems with the perforations. But what this gives is an immediate indication of where the match is poor. So in terms of history matching, these IJK locations can be saved in an ASCII file and put back into the simulator to try and determine why the match is poor. So this is a really sort of simple way of actually integrating the seismic and the simulation together. So what we've done here is look at the seismic as it's been back interpolated into the simulation grid. But what we can also do is compare the two different seismic data sets together as well. So I'm going to bring in the seismic impedance in depth and the synthetic, so we can look at the two different data sets together. So what we have now, if I just extend my window, is we have the 4D seismic impedance in depth, and I'm just going to pick up the synthetic and the original observed and just make a visibility cycling group. So now we can look at each in turn. So we're looking now at the synthetic, and now we're looking at the original observed. And you can sort of see straight away, just in a qualitative sense, that there is a reasonable match. And by using the visualization controls, we can look at these seismic as volumes. We can isolate high and low amplitudes. We can obviously move around the bars. So we can have a feel for basically how good a match it is. But to actually look at it in more detail, to actually to determine quite how good the match is between the observed and the synthetic seismic. If, for example, there's a particular channel of interest, it might be much more useful to do a sum of the amplitude over the channel for the two data sets and compare them again in a single object. So that's what I'm just going to show you now. So I'm just going to load a channel top. So this represents an interpreted channel in the data area. I'm going to put both of the seismic volumes back on. So what I'm going to do now is do, in effect, really a map view of the data. So for the original observed seismic, I'm going to do a sum of the property, and I'm going to use the channel as the top, and say I want it to be 30 meters below that channel, and I'm going to make a Z sum, which you can see here. Now I'm going to do the same for the synthetic. So again, do a sum of the property using the channel as the top boundary and make it 30 meters below. So again, if we pick up those two map views, so what we've done here is do a sum of the amplitude over the two 4D seismic volumes. So the important thing to be aware of here is that the data is still 4D. So we've got the 4D response, we've got the calculations for every time step. So now we have if we do the visibility cycling, you can see there is there's a more of a match in the upper fault block than in the lower, but not too bad a match. What would be really useful now is, rather than just observing them qualitatively, to actually be able to put them into the same object and do statistics on them, and that's exactly what we can do. So if I pick the original bandwidth, and again, I can import the synthetic into the same object. So if I turn now off the synthetic, we've now got, in the same 4DV, we've got the original observed seismic impedance and the synthetic seismic. And I'm just going to change the color just so that we can see that with the white it's more difficult to isolate points. I'm just going to put a different color table on. So we now have, for this particular channel, we've now got the seismic from the observed seismic and from the synthetic in the same object. So again, we can go back to the statistical tools and do a scatter plot of the synthetic against the 4D seismic. And again, do the regression line, the sigma lines. And again, it's a reasonable match. I mean, what is interesting is, having gone an entirely different route to generate the seismic, we've got a pretty good correlation between the original seismic and the synthetic seismic that we've calculated. So we could again select points that are poor matches and see exactly where they fall. And often these will be alongside potential transmissibility barriers, alongside faults, along ridges within a particular data set. But this just gives you very, very quickly a means of identifying where your data correlates well and where the correlation is poor. So this is looking very specifically at the seismic and simulation integration. But obviously this type of approach could be used for any of the other sorts of temporal data that you're using as part of history matching. And it's one of the things that I think is really lacking in the oil business, is this capability to integrate data that has come from different sources into the same object, and being able to do true statistical deterministic workflows from that data. So, in conclusion, I think the argument for 4D seismic has been made very eloquently already today, and there's huge benefits in terms of using 4D seismic. But to make it worthwhile, it's not just enough to have the data available, it's actually then got to be used effectively. It plays a very vital role in history matching to ensure the predictive simulation models, and therefore the reservoir management is on track. If the match is poor, the information must be quickly and easily assimilated, and any discrepancies identified, understood, and used for future planning. One of the things Habib mentioned earlier is that the turnaround from getting the seismic and using the seismic, to make it worthwhile, you have to have a quick turnover to make it worthwhile. And the discrepancies could be geological, but they can also be engineering issues. And by identifying any problems, if things are not as expected, it's really key to have these identified early. So you need to have a system where you can assimilate all this information in a very quick and easy to use way. So the capability, I'm coming from the visualization side. The capability to visualize and quantify these variations is key to effective reservoir management. There is no point in just having the data and not using it. And that's true not just in the 4D seismic world, but across the whole range of oil and gas applications. One of the areas that I work with considerably is with MPT data. And what amazes me is that MPT data and well data is often not amalgamated together. So often wells are drilled not using all the information available, and often with very dire consequences. Actually knowing where things are and being able to use all the data that you have available at your disposal makes a huge difference in terms of your reservoir management. Well, I hope my presentation today has persuaded the audience of the merits of a truly integrated approach. Thank you very much.
Thanks very much. And it's all going on in here?
Yeah.
Yeah?
Yeah.
There's no big machine that you
No,
brought
this
in and
is
parked
all,
for the day?
yeah,
or?
no. I mean, in fact, the system that I'm showing today is very portable. It can be based on Linux or Windows, and it's very, very easy to move from site to site to the rig, yeah, to finding petroleum. Doesn't require, yeah. It's
Doesn't it require you to do mischief with video game cards or
no,
something like that?
No,
Okay.
just standard Windows.
Okay.
Yeah.
Anybody got any questions? All right. Ian, please. Yeah. I saw a finger waving there. It's a line of grey hair between David Gowan and yourself. See, it's
yeah, I'm hiding behind David here. Yeah, thank you. Lovely paper. One of the nice papers I saw at the Copenhagen Convention this year was by one of the Shell staff, Floricic, doing a probabilistic inversion of multiple 4D images, multiple 4D data sets, converging his synthetic data set to his real data set using some sort of a Monte Carlo type of approach, Metropolis algorithm. So does your package do the same sort of thing?
Well, in fact, because it is, I mean, I was using real data as part of the demo. I think if you've got a system that behaves as quickly as that, doing multiple realizations is a very realistic possibility. We do have provision for doing some multiple realization, but actually trying to get, if you're generating synthetic seismic, trying to get the best match, it's actually a good way to go, to actually be able to do multiple scenarios and see which best fits your observed seismic. So yes, we do have provision for multiple realization.
okay.